Hello, my dear students. Good evening, all of you. Welcome to India's most comprehensive e-learning platform, that is Byjus Exam Prep. So this session is very important session for all of you. You might have already gone through the title of this particular session, a Formula 1 session. You have been attending so many classes, right? Today we are going to discuss the network theory, all formulas, okay? Today and tomorrow, 2 days we are going to spend. Today's session, we are going to discuss DC circuits and AC circuits in the network theory, the most important formulas which are going to be helpful for all of you, okay? I guess you're all going to take GATE 2023 or GATE 2024, whoever it might be. Now, these formulas are going to be very much helpful to all of you, okay? So before we enter into the formulas discussion, let me give my introduction. I think some of you might be new people, okay? You might be not aware of my profile, right? So let me give you briefly. My name is Dr. Muneender Sir. I did my master's and PhD both from NIT Warangal. I have 22 years of experience. My area of expertise is network theory, control systems and power systems. I did my master's and PhD both from NIT Warangal, and I presented some of my research articles in the international conferences of IEEE, okay? At USA, Hong Kong, Malaysia, Korea, and Singapore. I taught more than 250 batches across the country, none for GATE, ESC, PSUs, and guided, motivated more than 2 lakh students by visiting more than 500 plus engineering colleges or universities across the country, okay? I'm also supervising 4 PhD scholars on the most important and advanced topic called smart grid technology using artificial intelligence techniques. So this is all about me, and now before we get into the actual topic, okay, of the DC circuits and AC circuits formulas, okay, so I would like to appeal all of you to subscribe our YouTube channel so that whenever you, okay, come across the new series like this, similar to this, or whenever we give the lectures on the YouTube, free lectures, you'll be getting the updates, you'll be getting the notifications. You understand, all of you, okay? So please subscribe immediately, because I'm going to take in future certain important topics on control systems, power systems, and network theory again, okay? So those notifications you are going to get. Well, one more important announcement here, that is you are going to get 90% scholarship test if you, up to 90% scholarship test if you score well in the exam. That is to be held on 29th October, Nana. Okay, 29th October at 8 p.m. Don't miss this chance. If you're a newcomer, okay, or trying to look for a best coaching institute, obviously BYJU'S Exam Prep is one of the best coaching institutes in India. Okay, India's most comprehensive learning platform. You have all best faculty, but at the same time you'll be getting good amount of scholarship, that is up to 90% scholarship based on your score in the scholarship. That is held on 29th October at 8 p.m. Nana. Okay. So now, let's get into the DC circuits first. So DC circuits generally we divide into 2 important topics. One is of fundamentals. The other is DC theorems. Got it, all of you? Okay. Fundamentals of DC circuits and DC theorems. In the fundamentals of DC circuits, including node analysis, mesh analysis, current division, voltage division, source transformation, star delta transformation, okay? Some problems on KCL, KVL, current division, voltage division, network reduction. Yes, and all of these important topics will be covered. And whereas in the DC theorems, we are going to discuss what superposition, Thevenin's theorem, Norton's theorem, maximum power transfer theorem, okay? These are all very, very important theorems. Of course, there are many other theorems, but whatever is important for the exam point of view, I'm going to discuss in this particular session. Okay? I'm sure that if you stay tuned till the end of the session here, okay, till the end of this particular session, I'm sure that you guys are going to get maximum benefit, because I've been teaching this particular subject for the past 22 years. I know which particular formula is important for your exam. So I'm going to give you that in a step-by-step manner, easy manner. I'm going to explain also each and every formula where you are going to apply, okay, how it is going to be useful, and all those things I'm going to discuss. So today we are going to spend on DC circuits. and AC circuits. And tomorrow we're going to spend on transient analysis, most important interesting topic, Nana. Okay, and also the two-port networks, and of course the remaining. Okay, so therefore let's start with now the fundamentals of DC circuits. Okay, the first chapter is what? DC circuits, and the first topic in that particular one is about the fundamentals of DC circuits. So we all know the Ohm's law, which we apply to the resistor, inductor, and capacitor. So generally we express the Ohm's law is equal to what? VR of t is equal to IR of t into R. Yes or no, all of you? Okay. And similarly, for the case of inductor, VL of t is equal to L into DIL of t by dt. Okay. So we can also write it down like, VL of t is equal to L into slope of IL of t karunana. Okay. Sometimes, a straight line is given. You can simply find the slope of it. Okay, you will get the DIL of t by dt. Okay, if you multiply the DIL of t by dt into L, then you will be getting what? VL of t. Similarly, I can also get here IL of t can be written as, generally people miss this particular component in the formulas, but in the exam, the problems are coming based on this particular one component or this particular component also. IL of t naught plus 1 by L integral VL of t dt. You understand, all of you? Okay. What is this IL of t naught, Nana? This is called initial current. What is it called? Initial current. This is called initial current. This integration, whatever the integration you have mentioned, okay, integral t naught to t VL of t dt can also be written as what? Area under VL of t, okay, over the interval that is t naught to t, of course, plus the initial current you can write. So it's very, very important, okay. The first derivative term DIL of t by dt can be written as a slope, and the first integration, okay, over two boundaries, that is t naught to t, can be written as area under the curve. What curve actually you are taking here? VL of t is the voltage, okay, across the inductor. So area under VL of t can be taken. Finally, this formula is very important here, okay. So phi of t is equal to what? L into IL of t, obviously, where L is nothing but what? N square mu A by L, okay, small l. You understand, all of you, okay? N is nothing but what? Number of turns of the coil. Mu is the permeability. A is the cross-sectional area. L is the length of the coil. Yes or no, all of you, okay? Well, now coming to here, capacitor. When you take the capacitor, obviously when you take the capacitor, what happens here? C, and this is VC of t. Okay, this is IC of t, obviously. Okay, then IC of t or I of t can be taken as what? IC of t is taken as C into dVC of t by dt. Okay, and this particular one can also be expressed again what? A slope. Now similarly, VC of t can be written as VC of t naught plus 1 by C integration t naught to t IC of t dt. You understand, all of you? Okay, and I told you already that this is coming under what now? The area under the IC of t over t naught to t nana. You got the point, okay? Now Q is nothing but C into V, and C can be expressed as alpha epsilon naught by D, where alpha is the cross-sectional area of each conducting plate, and D is the distance between the plates, and epsilon naught is the, okay, permittivity. Yes or no, all of you? Okay, right. Now you can find, you know the KCL. I think I don't have to explain that KCL, algebraic sum of the currents at any instant of the time is 0. Okay, and which is also can be expressed as what, Nana? Sum of the entering currents is equal to sum of the leaving currents. Usually I take the leaving current as positive and entering current as negative. Some people take reverse. It doesn't make any difference, because if you multiply the equation by -1, does it make any difference, Nana? It does not make any difference. Now coming to the KVL, algebraic sum of the voltage in a particular loop is 0. In any loop, in any closed path is 0. Okay? And the most important point to be observed here is that if you have 100 nodes, okay, in a given circuit, at each and every node, at all 100 nodes, the KCL must be satisfied. Okay, otherwise the circuit is said to be invalid. If there are 100 loops, let us say, okay, and in every loop, the Kirchhoff's voltage law must be satisfied. You got the point, okay? Otherwise, the circuit is invalid, Nana, okay? Well, now, let's come to the network reduction because we need to reduce the networks. The ultimate objective of the network theory is what? Network analysis. We want to analyze the networks. Network analysis means for a given network, you must be able to find the current, voltage, power everywhere in the given network. Yes or no, all of you? Current through resistor, current through inductor, current through capacitor. Similarly, voltage across the inductor, voltage across the capacitor, voltage across the resistor, like that. Everywhere you must be able to find. Once you know current and voltage, can't you find the power? Yes, you can. Yes or no, all of you, okay? Then, but to find all these things, the reduction of the network is also very, very important. Okay, so let's have a look at now the series combination of the resistors. I start my discussion with the resistor, and then later, of course, I can also discuss the inductors and capacitors later on. Okay, first let me start with, because I'm dealing with the DC circuits, fundamentals of DC circuits first. So in the DC circuits, I generally don't take the problems of what the inductors and capacitors. I deal with the resistor just now. Okay, now tell me here, when n number of resistors are connected in series, what is the total resistance, Nana? The total resistance is nothing but what? Okay, the equivalent resistance can be taken as what, Nana, here? Hi everybody, hi Anil, hi Bhaskar Lakshmi, okay, hi Sagar Roy, okay, hi everybody, hi Ravi Shankar. Okay, if you have any doubts, please, yes sir, where can we get the PDFs? Okay, don't worry, the PDFs will be taken care by our team, okay? They will be sending you. But you first keep tuning to the class. I'm sure that you're going to get maximum benefit out of it. Okay, so let's try to discuss now here. If you have any doubts, please keep posting in the comment box. Okay, I will definitely clarify your doubts. Jagadish Reddy, hi everybody, hi, good evening. If I miss anybody, a big hi to everybody. Okay, fine. So now RAB is equal to what? Summation I is equal to 1 to n Ri. And the most important point to be noted down is that when you find the series combination of resistors, the total equivalent resistance will be the higher than the maximum value of, higher than what? Higher than or greater than the maximum value of all these resistances. For example, you are taking 2 and 3 series combination. What is this value? None of 5. In this, what is the highest value? 3. The total equivalent is 5. 5 is greater than 3. This is very, very important observation. Okay, this observation is very important to solve the problems, okay, in a simple manner sometimes. Okay, sometimes some 1-mark questions can be easily solved. Okay, now what about the conductance, Nana? Conductance is always a reciprocal. Yes or no? RAB is nothing but 1 by GAB. Okay, and RA is nothing but 1 by GA. Finally, I'm taking GAB. Therefore, a reciprocal of summation I is equal to 1 to n, okay, 1 by GI. Now, the total equivalent conductance GAB will be, okay, less than the lowest value of G1, G2 and so on Gn. For example, 6 Siemens, okay, 6 Siemens and 3 Siemens are connected in series. What is GAB, Nana? G1, G2 by G1 plus G2. What do you get, Nana? 6 into 3 by 6 plus 3, it is 2. Look at this. This equivalent value is less than this lowest value of that G1 and G2. Yes or no, all of you? So that's very, very important point to be noted down. Okay? And the similar logic you can apply for the parallel combination of resistor and series and parallel combination of inductors, series and parallel combination of capacitors. Similar logic you can apply. Okay, and resistance relations and inductor relations will be same, and conductance relations and capacitance relations will be same. You understand, all of you? Okay, the formulas look very similar. Capacitor formulas look similar to the conductance formulas. Inductor formulas look similar to what? Resistance formulas. Got it, all of you? Okay, so please keep posting. Okay, thank you. Okay, thank you, Jagdish, and somebody like electrical I don't know what is your name, please tell me. Thank you so much. Yeah, now I would like to actually find the voltage across the kth element when n number of elements are connected in series. So generally you people read for 2 elements, right? But I'm generalizing here for what? N number of elements connected in series. Now I would like to find the voltage across the kth element. So what happens here when I just find the voltage across kth element? The Vk is equal to Rk by summation I is equal to 1 to n Ri into the total voltage that is applied. Or if you are interested to find the voltage across kth capacitor in terms of conductance, Nana, 1 by Gk by summation I is equal to 1 to n, 1 by Gi into V. Hi Ravi Shankar, hi. Okay, so hope you're all following. Please respond quickly in your comment box. If you don't understand, please let me know. Whatever the doubt you have in the networks, please keep posting. Okay, today and tomorrow, anyway, we are spending a lot of time on formulas completely. Okay, it's a quick revision for all of you. Okay, generally, if you want to revise on your own, it will take a lot of time, Nana. But we framed everything in a proper order and trying to give you everything. If you attend the class carefully, I'm sure that you're going to get maximum benefit. So kindly respond quickly in your comment box. Are you able to follow? Okay, if you're able to follow, please put S, okay, in the comment box. Thank you so much. So now, well, I think you understand now in terms of both resistance as well as what, Nana? Conductance. So this is very simple and important formula for n number of elements connected in series. What is the voltage across the kth element, both in terms of resistance as well as conductance. Now coming to the parallel combination of resistors. Okay, G1, G2 and so on, Gn I am taking, I1, I2 and so on, In. When elements are connected in parallel, what happens? Okay, voltage will be same and current will be dividing. Current divides. Yes or no? Whereas in case of series combination, okay, in case of series combination, what happens here? Tell me. Current will be, tell me all of you, current will be same, but voltage divides. Voltage divides. Is it okay, all of you? Series combination, yes, capacitance has GAB. No. See, I'll tell you here, Bhaskar Lakshmi, yeah, capacitance formulas and conductance formulas look similar, I am telling you. Okay, they look similar. That's all. Okay, so same formulas you will see, like when capacitor connected in series, CAB is equal to C1 C2 by C1 plus C2. GAB is also G1 G2 by G1 plus G2. Likewise, you have a similarity, like the formulas look similar. That's what my intention is. Okay, well, now coming to here, GAB is equal to, yes, Milind, hi, yes, hi. So GAB is equal to what? Here, summation simple. Conductance can be added when elements are connected in parallel, Nana. Okay, I is equal to 1 to n Gi, and GAB, generally the equivalent conductance will be greater than the highest value of the conductance S. Similarly, when you find RAB, it is less than the lowest value of R1, R2 and so on Rn. So this is very, very important to be remembered. Okay, this will help you to directly answer certain questions in a 1 mark. Okay, and what about the current flowing through, because current is getting divided. When current divides, I would like to find the current through kth element. Okay, what is current through kth element? Gk by summation I is equal to 1 to n Gi into I is equal to 1 by Rk by summation I is equal to 1 to n 1 by Ri into I. This is what the total current I, and what is the current flowing through the kth element. You understand, all of you? Okay, now you can apply when there are 2 elements. Okay, how the formulas can be applied is very easy for you. So always remember, for n number of elements connected in series, n number of elements connected in parallel. It will be easy for you when you have 3 elements, 4 elements, 2 elements. It will be easy for you. Got it, all of you? Okay, well, source transformation, I think all of you are aware clearly, right? When a practical voltage source is there, it can be converted into practical current source. What is a practical voltage source, Nana? A voltage source with a series resistor can be considered to be what? A practical voltage source. Okay, this is individually ideal voltage source. This is a series resistor. Okay, then ideal voltage source with a series resistor can be called as what, Nana? a practical voltage source. Ideal current source with a parallel resistor can be considered to be what, or can be called as what? Practical current source. Now, according to source transformation, a practical voltage source can be transformed into a practical current source. You understand, all of you? Okay? Well, now coming to star delta transformation. I think all of you are able to follow. Okay? Now coming to star delta transformation, first we consider the delta to star. Okay? First we consider what? Delta to star. So it is a delta network and this is a star network. Delta network consists of three elements which forms a common loop. Star network consists of three elements with a common node. Delta consists common loop or a loop, let us say, or a closed path. But here star network consists of a common node. You got my point? Okay, well. So now RA is equal to, I would like to know this RA, RB, RC in terms of RAB, RBC, RCA. Okay, because RA, RB, RC are the unknown values. RAB, RBC, RC are the known values. Okay, I am interested to find the unknown values in terms of the known values, right? So RA is equal to, okay, RAB into RCA by RAB plus RBC plus RCA. Similarly, the beauty of this formula, you can see the denominator does not change. Look at the same denominator. RB is equal to RBC into RAB, okay, by the denominator same. RC is equal to RBC into RCA, the denominator same. It is easy to find even RA, RB, RC just simply drawing a star network inside the delta network. Look at this. When do you apply star delta transformation generally? In the reduction? Generally in the reduction, when do you apply the star delta transformation? Star delta transformation is applied to simplify the network, yes or no? When do you apply? Can anybody answer in the comment box, please? I'll be very happy to see the answers. Suppose, for example, this is the network given. For this, do you need any star delta transformation? You don't require, right? Because these two are in series, the result is parallel with this element and the result is in series with this particular element. Yes or no? Okay. But suppose if I give you another network, something like this. Yes. Bhaskar Lakshmi, very good. You don't require star delta transformation. But you tell me, for this you require star delta transformation or not? Tell me. Suppose if it is 1 ohm, this is 2 ohm, this is 3 ohm, this is 4 ohm, this is 5 ohm, let us say. All elements, how they are connected. Okay, when neither series nor parallel. Hema, very good, Nana, very good. If you look at this particular circuit, when all elements are neither series nor parallel, okay, there you cannot apply this series and parallel combination, right? When neither series nor parallel means what? Series formulas are not applicable, parallel formulas are not applicable. In such cases, you have to go for what? Star delta transformation. You understand, all of you? Okay, well. So now tell me here, delta is getting converted. So star delta transformation is applied when all elements are neither series nor parallel. You agree, all of you? Okay, well. Now what about this one? This is now RA. It is easy to remember, okay? Multiplication of adjacent elements by total sum of all the elements. Multiplication of adjacent means what, Nana? RAB into RCA. Okay, sum, that's it. Similarly, this one also, RBC means, okay, yeah, this one I would like to find. This is RB. Multiplication of RBC into RAB, because these two are adjacent now. This is what RC now. RC is nothing but what? Okay, multiplication of adjacent, that is RCA and RBC. Divided by summation, summation of all three elements in the denominator is same. It remains same for all three quantities here. Okay, so it is very easy to remember. Similarly, the same formulas can be expressed in terms of conductance also. I told you already, you are going to deal with the capacitors and inductors. Okay, there also again you get the star delta transformation. There also you will get all neither series nor parallel combination. You understand, all of you? Okay, there the formulas of the capacitors, okay, will be similar to the formulas of what? The conductances. So that is why I am expressing here GA is equal to GAB into GBC plus GBC into GCA plus GCA into GAB by GBC. Similarly, GB, the numerator does not change here. That is the beauty of it, okay? And GC is nothing but the numerator does not change, But GB will become here what denominator you will get GCA, whereas here GAB. Simple to remember the formula. Now second case is what star to delta. This is star, now this is delta. Now I'm going to construct a delta for the given star. This is nothing but RAB, okay? So RA into RB plus, RB into RC plus, RC into RA by, okay? What is that? Opposite to this particular element, that is nothing but RC. Here you can see RC. Similarly, the numerator does not change here, okay? And RAB, then denominator here RC it becomes RBC, RA it becomes RCA, then RB it becomes in the denominator. The numerator does not change in the case of star to delta, in the case of resistors. Now coming to the conductances, okay, I told you already that conductance, the formulas in terms of conductance and resistance must be on your fingertips. You can't get any doubt in that. You can't search for the formula in the exam. It takes unnecessarily, it's going to kill your valuable time. That is why the formulas must be on your fingertips. Okay. Oh, GBC, GCA similarly. Yeah. So these are all very, very important formulas for star delta transformation. Okay. Star delta transformation you're going to apply when to a network in order to reduce when all elements are neither series nor parallel. Is that okay, all of you? The circuit is complex with only one resistor connected with voltage. Yes. Ravi Shankar, of course, but when all elements are complex means what, Nana? Complex means what? With only one resistance connected with voltage. The circuit is complex. What does it mean? Complex means what? Complex means you are not able to recognize the series and parallel combination. All elements are neither series nor parallel. It looks complex, right? When elements are connected in series and parallel, if you are able to find, it is not a complex network. You can easily reduce that. But when it comes to all elements neither series nor parallel, certainly it looks very complex. In such cases, we go for what? Star delta transformation. Clear? Well, now another 10th important formula. The current can be stated as what? Time rate of change of charge. Nothing but what? Slope of Q. This is very important. There is no need to differentiate all the time for the given function. Sometimes the waveform is given like this. Okay, this is what the charge and charge versus time. I would like to find the current. Okay, this is what actually some 10, let us say. This is what some 0, 2, 4, let us say. I would like to find the current. So what do you do here? Generally people try to derive the expression for this particular one, line passing through the origin. Then there's a straight line with a negative slope. Okay, then you will get Q of t. Then after that you will differentiate Q of t with respect to time. Then you will get the current. But don't do that. Okay, it's going to kill your valuable time. Instead of that, you can simply find the slope of it. What is the slope, Nana? The slope is here, this is 10, this is 2, 10 by 2, nothing but what? 5 ampere. That's it. If it is in coulombs and it is in second, then simply you will get the slope is nothing but what? 5 amperes. What about this slope? Here, this is 2, 10, and this one is what? 4, 0. The slope will become now simply, okay, 0 minus 10 by 4 minus 2. So what do you get? Tell me here. What do you get? Tell me here. Minus 10 by 2, nothing but minus 5 ampere. So one is a positive slope, the other is a negative slope. Like this, you can simply find using the slope of Q of t. Current is nothing but the slope of the charge. But the charge is nothing but what? Q of t naught, okay? Integration t naught to t, I of t dt. Here sometimes if t naught is taken as 0, then this formula can be expressed as what, Nana? Q of 0 plus integral 0 to t, I of t dt. I can also express, this one can be called as what, Nana? Initial charge. What do you call it? Initial charge, Nana. Initial charge. Ravi Shankar, yes, great. The slope is in the square shape, then how we calculate? Okay. Then the slope will become 0, na? For a square, what happens, Bhaskar Lakshmi? Okay, if you have a square shape, the slope is 0. Yes or no? What is the slope for this? Tell me. Slope for this one is 0, na? So don't worry about that, okay? Well, suppose if there are nonlinear functions like exponentially increasing, exponentially decreasing, here it is very difficult to find the slope. In that particular case, you have to find the charge expression is required. Then you have to differentiate that with respect to time. There is no other option. But when you have, a triangular, rectangular, trapezoidal, straight lines where you can find the slope, you can comfortably apply the slope concept. You understand? When you have nonlinear curves, sinusoidal function, exponential functions, exponential waveforms, definitely you require the expression for that particular waveform. Then you have to go for the differentiation. I hope you understand, Bhaskar Lakshmi. Please respond quickly on the comment box if you are following. Okay, I can move ahead. Well, now q of t can be expressed as what? Now q of 0 plus integral 0 to t I of t dt, which can be written as initial charge plus area under, very good Bhaskar Lakshmi, very good Hema. Okay, and okay, area under I of t from 0 to t. Hope you are following this formula, right? Okay, simple formulas. So when charge is given, current is asked, go for the slope calculation. When current is given, charge is asked, go for the area under the curve. But don't forget to include this particular initial charge. In case, if the initial charge is not mentioned, and it is also not possible to find the initial charge for the from the given data, then certainly you must assume that initial charge is 0. You understand, okay? There is no chance to find, and that is not given directly or indirectly. Sometimes he will give you indirectly initial charge. For example, capacitor you take, he will give you initial voltage and capacitance. Then initial charge is known because Q is equal to C into V. Yes or no, all of you? So like that, if indirectly is given, you have to find it. If it is not given and there is no chance to find, certainly you have to assume that initial charge is 0. Okay, but when you write the formula, better you remember like this only, because most of the people, they have a tendency to directly ignore this particular charge. Okay, but charge is mentioned, therefore the answer you will get a different answer. You will get a wrong answer. You got it, all of you? Okay, following all of you, please respond in the comment box, all of you. Okay, well, right now power formula, you know that time rate of change of energy. Yes or no? Okay, time rate of change of energy, nothing but what? Voltage into current, because voltage formula also you know very well. What is the voltage formula? Okay, work done on unit positive charge, dW by dQ. This is very important formula, dW by dQ. Okay, work done on unit positive charge to move that unit positive charge from one point to another point against the electric field. That is nothing but the voltage or the potential difference, you can call it. Yes or no? Now, power is nothing but what, Nana? dW by dt, time rate of change of energy or time rate of change of work done. Okay, work done per second you can call it. But dW by dt can also be written as dW by dQ and dQ by dt. But dW by dQ is nothing but the voltage just now we have discussed, and dQ by dt is nothing but current we have discussed. That is why power is always the product of voltage and current. Following all of you? Okay? Well, now coming to that energy, knowing the, again I can express that here. I can express that dW by dQ, dW by dt is nothing but what? Slope of energy, slope of W of t. So energy is given or work is given, you are asked to find the power, go for the slope calculation. But power is given, okay, you need to find the energy, then go for the area calculation. This is nothing but what? Initial energy. If T0 is equal to 0, then W of 0 plus integral 0 to T P of T dt. This is what W of T. But I told you already that this is the area. Okay, W of T0 plus area of P of T over the interval what? T0 to T. If T0 is 0, then you can put 0 and then you can proceed further. So power is given, energy is to be determined. You have to find the area calculation. You have to go for the area calculation. On this particular formula, a couple of times the question was asked in the gate. Okay? Well, now, shall we go with the DC theorems, Nana? Okay? Node analysis, mesh analysis, I think the formulas are very clear. Okay? Node analysis, mesh analysis also. Suppose you take mesh analysis. How many number of equations required to solve the network? Tell me, all of you. If there are fundamental loops, L number of loops are there. Okay, L is equal to B minus N plus 1. Yes or no? Where B is the number of branches, N is the number of nodes, L is the fundamental loops. Now, number of fundamental loops and number of equations are required, okay, to solve the network will be same. Where L is standing for what? L stands for what, Nana? Fundamental loops. What do you call them? Simply not loops, okay? Fundamental loops. Fundamental loops. L is nothing but what? Fundamental loops. You understand, all of you, okay? Suppose if there are any current sources, what are the minimum number of equations required to solve the network using the mesh analysis? Minimum number of equations using mesh analysis is equal to fundamental loops L minus number of current sources. Number of current sources. Okay, the minimum number of equations required to analyze the network. The minimum number of equations required to solve the network will be number of fundamental loops minus number of current sources. Okay, minimum number of equations required to solve the network. But when it comes to the node analysis, okay, if there are n number of nodes, minimum number of nodes, then the minimum number of equations required, how many, Nana? N minus 1. Because one node we are selecting it as what? Reference node or datum node or zero potential node. So n minus 1 equations required. Got it, all of you, okay? Well, in the case of mesh analysis, number of equations is equal to number of fundamental loops. But if there are any number of current sources, if there are any current sources in the given network, then yes, if it has a current source, Ravi Shankar, yes, that's what I'm trying to explain, Ravi Shankar. I think you understand that now. Minimum number of equations required using mesh analysis in case of current sources, L minus number of current sources, Nana. But whereas in node analysis, okay, number of current sources are there or not, doesn't matter. N number of nodes, N minus 1 equations are enough. You understand, all of you? Okay, well. Got it? Okay. The advantage in the mesh analysis, you know, when there are number of current sources, then the number of equations will come down. You understand, all of you? Okay. But disadvantage with the mesh analysis, you know, it is not applicable to the non-planar networks. Mesh analysis is not applicable to non-planar networks. You understand, all of you? Okay. Whereas node analysis is applicable to both planar as well as non-planar networks. Node analysis is applicable to both planar networks and non-planar networks, but mesh analysis is applicable to only planar networks. It is not applicable to non-planar networks. You understand, all of you? Okay. Well, that is the greatest advantage. Okay. Which one of the following statement is true? Like that the question will come in case of mesh analysis. You understand, all of you? Okay. It is applicable to planar networks or non-planar networks. You understand, all of you? It is applicable to only, I hope you understand the point. What are the advantages of the node analysis over the mesh analysis, if somebody is asking? Node analysis is advantageous over the mesh analysis. In what point of view, Nana? In what point of view? It is applicable to the planar networks as well as non-planar networks, whereas mesh analysis is not applicable to the non-planar networks. You understand, all of you? Okay. Well, now let us see theorems. DC theorems. Superposition theorem. Superposition is applicable when the circuit consists of what? Multiple sources. Okay. Superposition is applicable when the circuit consists of what? Multiple energy sources. Multiple excitations. Multiple energy sources. Multi-energy source network we can call. So whenever a system consists of multiple inputs, I mean more than one input, there you can apply the superposition theorem. Superposition is not just applicable to the electric circuits. Okay, you can apply to any mechanical system, chemical system, biological system. Okay, any system doesn't matter. Wherever you have more than one excitation, there you can apply comfortably. Got it, all of you? Okay. So according to superposition theorem, actually any circuit that is given a linear circuit, you understood all of you? I mean, you have circuits, right? You have different circuits. Okay, given circuit is a linear or non-linear. How do you define that? A linear circuit and non-linear circuit. Linear element, non-linear element we can define, because an element which obeys the Ohm's law is called linear element. An element which does not obey the Ohm's law is called non-linear element. But what about, yeah, sir, the planar network nothing but a 3D shape. No. Planar network 3D shape, not like that. No. Planar network means what? For example, you have a network like this. This is R1, this is R2. Is it a planar network or non-planar network? Can anybody answer this? Please quickly, is it a planar network or non-planar network? Planar network means a network that can be drawn on a plane with no crossovers. No branches crossing over others. Okay, with no branches crossing over other. You tell me now. You have any crossover in this? Is it a planar network or non-planar network? Yes? Is it a planar network or non-planar network? Tell me. A planar or non-planar? Anybody answer please quickly? Planar. Bhaskar Lakshmi is saying planar. Non-planar. Why it is non-planar? You are seeing the crossover, but just by seeing the crossover you can't decide it is a non-planar. What you have to do is, first you have to, okay, redraw the network. Okay, look at this. If this is A, this is B, this is C, this is D, look at this. Now can I draw the network again, redraw the network something like this, Nana? Tell me. Okay. Look at this. This element, what you call R3, and this is what R4. Can I draw R4 something like this again? Can I redraw like this? Can I redraw the network like this or not? So once I redraw the network, Hema says non-planar, Ravi Shankar says non-planar, because by definition you are going. You are just going by definition, Nana, but you have to apply your common sense that whether I can restructure the network, redraw the network or not. I am able to redraw the network here. When I redraw the network, do I find any crossovers? Please respond quickly, all of you. I am not finding any crossovers, yes or no? Therefore, it is a planar network. Okay? No 3-dimension, okay? There is no 3-dimension at all. Yes. You understand, all of you? But whereas, suppose if I give you something like, some network like this. I'll come back again to superposition. Please be patient, okay? Someone raised the doubts. That's why I'm trying to clarify here. Look at this. You have to respond to this. Is it planar or non-planar? Is it planar or non-planar? R1, R2, R3, R4, R5. This is R6. Please respond quickly. Ravi Shankar, Hema. Okay. Bhaskar Lakshmi, please respond quickly. Is it planar network or non-planar network? Quickly respond, please. Non-planar, Bhaskar Lakshmi. Abhishek Singh, good evening. Please respond quickly here. Non-planar. Non-planar, you are saying. Ravi Shankar. Kiriti, okay. Non-planar, 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 Hema, Ravi Shankar. Okay, look at this now. So again, you did a mistake. I told you have to redraw the network and then try. First, you make an attempt. First, you make an attempt whether you are able to reconstruct or not. First, you make an attempt. Look at this. Suppose if you have, this is R6, right? This is R7, let us say, right? This is R7. The problem is with R7 and R4, right? Both are crossing over other. R6 and R7, R6 is crossing over R7 or R7 is crossing over R6. But can I say something like this? Look at this, all of you. Carefully you observe. This point and this point, both are operating at same potential or not, because this is a zero resistance path. Yes or no, all of you? Now, can I take this R7 and connect across this R4? Do you have any problem? If I just redraw the network, I just disconnect this element and construct like this. Now you tell me, do you find any crossovers in this now? Do you find any crossovers? No, right? So tell me now, is it a planar or non-planar? Abhishek said planar, very good. Ravi Shankar is saying because it is already reduced. No, I'm not reducing. See, don't reduce and conclude that it is planar, non-planar. You can only reconstruct, you cannot reduce it. Very good, Ravi Shankar, you raised a very good point actually. You can't reduce, Nana. Okay, when network is given, okay, when somebody is asking you that, it is a planar or non-planar, you can't reduce and decide. No, you have to reconstruct and you have to reconstruct and conclude. You cannot reduce it. Okay, you have no right to reduce it. You understand? Okay, very good. Hema, I think yes. Now you got Ravi Shankar. Okay, very good, very good. Bhaskar Lakshmi, you understand, right? But I give you another important network here. The same network I can give you. Now hope you will easily answer. Look at this. Look at this. Look at this. Now you tell me, is it planar or non-planar? Coming now, coming to that only, okay? Non-planar example only I'm going to come now. Yeah, now you tell me. Now you tell me. Is it planar or non-planar? Quickly respond, please. Planar or non-planar? So one more questions might, you may get from any direction. Concept must be very clear. He will be asking you that, non-planar because it connects R8 to negative terminal, sir. Okay. Very good. Very good, very good, very good, Bhaskar Lakshmi, Hema, non-planar. Yes, exactly. You see now, even if you reconstruct, can you escape from the crossover? Please respond. The crossing over, one branch crossing over other, you can't escape. Look at this here. Even if I disconnect, because this point is very important for me as far as R7 is concerned. Now this point and this point both are not same because of this R8. There is some voltage drop across that. This point and this point both are not operating at same potentials. Both are at different potentials. You understand, okay? Now, if you want to reconnect that, you have to reconnect. In any direction you reconnect, definitely you have to cross over. Look at this. Again, one crossover is there. Look at this. So you are crossing over. One branch is crossing over other. You cannot escape from crossing over. One branch crossing over the other. So that's what I'm saying here. Planar, non-planar, that difference must be very clear. So what you have to do whenever the network is given, okay, in the network you will definitely see the crossovers. Okay, one branch is crossing over other, you will definitely see. Just by seeing that you can't decide it is a non-planar, what you have to do is you have to reconstruct the network, then you conclude whether the crossover can be eliminated or not. If it is eliminated, planar. If it is not eliminated, non-planar. If it is eliminated planar, that problem can be solved by both mesh analysis and node analysis. If it is not eliminated, it is becoming what non-planar. That problem cannot be solved by the mesh analysis, but can be solved by the node analysis. Clear, all of you? Please respond in the comment box, all of you. Yeah. After this formula session today and tomorrow, very soon I'm going to discuss how to solve the networks using simple techniques. Simple shortcut techniques. You become master in the network analysis, I'm telling you. Okay, node analysis, mesh analysis, minimum number of equations, how to identify. In less number of steps, how to solve the network. With less number of equations, how to solve the network. All those things I'm going to discuss. Okay, so you just please subscribe to channel because you can't get the updates from me directly. Only from the YouTube you are going to get. Okay, so I'll be definitely taking one important session very, very soon. So don't miss that session, I'm telling you. After that session, you can play with the networks. Okay, well. Okay, now let's move on to what? Theorems, okay? Superposition theorem. Yeah, now tell me. Superposition theorem is applicable to the networks which consists of at least two independent energy sources. At least two independent energy sources. Energy sources. Sir, there is one independent source, one dependent source. Can I apply superposition, sir? No. Not applicable. If you want to apply superposition to any given circuit, it should consist of at least two independent energy sources, Nana. This is the rule. You understand, all of you? Okay, well. Any circuit that obeys principle of superposition is called a linear circuit. Any circuit that obeys principle of superposition is called linear circuit. Otherwise, it's a non-linear circuit. An element which obeys Ohm's law is called a linear element. Bhaskar Lakshmi, non-planar is solved by node analysis, sir. Yes, exactly, Nana. That's what I was trying to tell you. Okay? Hema, it's clear, sir. Okay. Okay, Ravi Shankar, could you repeat? Where did you get the doubt, Ravi Shankar? I'm sorry, I missed your comment. Okay? Where did you miss that concept? Tell me. I told you clearly that when you're trying to eliminate the crossovers, if you are not able to eliminate the crossover, it is called non-linear, non-planar network. That can be solved by only node analysis. Planar network can be solved by both mesh analysis as well as node analysis. Is it okay, Ravi Shankar? Okay. Yeah, please respond, okay? If you still have a doubt, okay, I just share my Telegram group channel also, Professor Muneender Professor Muneender Gate. Please note down this. Because sometimes, discussion can't be extended in the... Oh, got it, Ravi Shankar, very good, okay. But if you still have any doubt, please. Professor Muneender Gate. This is my Telegram group channel. You can join in this and you can ask me any doubt. Okay, you can join this group. Okay, I just keep posting the sessions, whatever I'm going to take in the future, okay? Yeah, Professor Muneender Gate. It is open to everybody, you can join easily, right? Yeah. But please discuss only the subject, no other comments in that particular channel. Now coming to here, a superposition theorem. Superposition theorem statement is applicable to only current or voltage response, but not to the power. But power can be expressed in terms of current and voltage. And finally, okay, the power formula, when n number of independent energy sources are there, when P1, P2 and so on, Pn are the powers due to the individual independent sources, then what is the total power, okay, when all energy sources are acting simultaneously? The formula you have to remember is plus or minus root P1, plus or minus root P2 and so on, plus or minus root Pn whole square. It is very clear, when you have plus or minus, you have different answers for the power. Yes or no, all of you? The total power is not unique. You will get different values. Okay, if you take plus, minus, you will get one answer. When you take all plus, you will get one answer. When you take plus, minus, plus, minus, like that, you'll be getting another answer. Therefore, different answers you will be having for power. Current answer, okay, voltage response, current response will be unique, but power response is not unique. Okay, that is why he will be asking you in the exam, what is the lowest value of the power? What is the highest value of the power? Like that he will be asking you, okay, on superposition theorem. Whenever a problem is asked in the superposition, that too on the power, definitely you will be having more than one answer, Nana, because plus or minus is there. Is it clear, all of you? Okay. Now, superposition theorem, to understand, I told you already that any circuit that obeys principle of superposition is called linear circuit. Yes or no? Okay. What do you mean by linear circuit or linearity? Let's look at the linearity property. Linearity property is nothing but sum of two important properties. One is the homogeneity property, the other is what? Additivity property. What do you mean by homogeneity property, Nana? According to homogeneity property, the response is directly proportional to the excitation. That means what? When excitation is doubled, the response is doubled. When excitation is halved, the response is halved. When the excitation is multiplied by -1, the response is also multiplied by -1. Proportionate. The relation is what? Proportionate relationship. What is additivity property? Generally, additivity property is applied when you have more than one energy source, particularly independent sources in our electric circuits. You understand, okay? For example, if I naught dash is the response due to the first excitation, when there are two sources, I naught dash is the first excitation. For example, I have a 20 volt source and 10 volt source. Because of 20 volt source, I got, let us say, some 4 amperes. Because of response, I'm looking at the current, okay? I'm just taking current's response here. 10 volt source, there are two energy sources. One is at 20 volts, the other is at 10 volts. You understand? When 10 volt source is acting alone, the response was some 3 amperes. When 20 volt source was acting alone in the given network, the response was 4 amperes. You understand, all of you? Okay. Well, now this is 4 amperes is nothing but I naught dash and 3 amperes is nothing but I naught double dash. What is the total response? With an assumption that both the currents are flowing in the same direction, then I will be getting I naught is equal to, what is that, Nana? 4 plus 3, 7 amperes. Suppose if this particular source value is doubled, this source value is halved, becoming half. Here becoming doubled and halved. Then what happens? When 20 volt source is doubled, its corresponding response is doubled. That means what? 2 into 4. Okay, that means 2 into, this is I naught dash, this is I naught double dash. Okay, now what happens here? 2 into I naught dash, okay, plus half into, when 10 volt source is halved, its corresponding response, that is 3 ampere, that is nothing but I naught double dash will be halved. I naught double dash. This is nothing but I naught nu. This is I naught nu, Nana. The new response will be, okay, according to homogeneity property, when the source value is doubled, its corresponding response is doubled. Okay, according to homogeneity, when the source value is halved, its corresponding response is halved. Okay, therefore, you will be getting now 2 into 4 plus half into 3, okay, 8 plus 1.5, that is 9.5 ampere. Is it clear, all of you? Is it clear, all of you? Are you able to follow? Ravi Shankar, Bhaskar Lakshmi, Hema, okay, all of you are following, Nana? This is what the superposition theorem, and on this particular example only you are going to expect the questions in the GATE examination. Homogeneity property and additivity property are very, very important. On these only you are getting the questions. So far there are 3-4 questions on the superposition were asked only on this particular example that I have discussed today. Okay, well, so this power also very, very important formula, where P1, P2 and so on, Pn, when there are n number of sources, their individual power response are P1, P2 and so on, Pn, and the total power that can be determined here is with the simultaneous operation of all the sources will be plus or minus root P1, plus or minus root P2 and so on, plus or minus root Pn whole square. Okay, this is a very, very important formula, Nana. 1 mark question may directly come in the exam on the superposition theorem. Got it, okay? Well, if you have any doubt, please put in the comment box, okay? Bhaskar, Hema, Ravi Shankar and other people, Abhishek, okay, anybody, please just put in the comment box. I can definitely clarify your doubt. Don't worry. Got it? Okay. Shall we look at now the Thevenin's theorem here now? All of you? Thevenin's theorem. Thevenin's theorem. Any linear bilateral network, okay, any linear bilateral network can be replaced by an equivalent practical voltage source with respect to the load terminals, because there is a load. Practical voltage source is nothing but what? Thevenin's equivalent circuit, Nana. Thevenin's equivalent circuit. Got it, okay? Any linear bilateral network can be replaced by an equivalent practical voltage source. Practical voltage source means what? An ideal voltage source with a series resistor. Yes or no? Okay. This ideal voltage source value is called Thevenin's equivalent voltage or open circuit voltage. The resistance value is nothing but Thevenin's equivalent resistance. You understand, okay? Thevenin's equivalent voltage, how do you determine? Simply remove the load, find the voltage across the open terminals. That voltage is nothing but Thevenin's equivalent voltage or open circuit voltage, because you are removing, right? You are removing and finding, right? Therefore, it is called open circuit voltage, because the current becomes 0 here. IL becomes 0. Similarly, how do you find RTH, Nana? How do you find RTH? Tell me. The RTH can be determined. Remove the load. Find the resistance across the load terminals. Find the resistance across the load terminals. But before that, you replace all independent sources by the internal resistances. I hope you understand this. You replace all independent sources to be deactivated. What do you mean by deactivated? Energy sources deactivated, suppressed, replaced by their internal resistance, all are same, Nana. Okay? Voltage source is replaced by the short circuit because its internal resistance, ideally speaking, 0. Resistance 0 refers to short circuit. Current source are replaced by open circuit. Voltage source are replaced by the short circuit. Current source are replaced by the open circuit. Following all of you? Okay. Following all of you? Very good. So replace all energy sources by their internal resistances. Then you find the resistance across the terminals where the load is removed. Here is the load removed, right? Here is the load removed. Therefore, find the resistance across the terminals where the load is removed. Well, I think the formula is very clear. Once you find the Thevenin's equivalent, IL is nothing but VTH by RTH plus RL. And of course, VL is nothing but IL into RL, nothing but RL by RTH plus RL into VTH. I hope you understand this. Clear? If you have any doubts, please mention in the comment box. Please mention in the comment box, okay, if you have any doubts. Right. Shall we go with now Norton's theorem? Norton's theorem. Norton's theorem. Any linear bilateral network can be replaced by an equivalent practical current source with respect to the load terminals. With respect to load terminals, it can be replaced by a practical current source. Practical current source consists of an ideal current source with a parallel resistor. This ideal current source value is nothing but IN or else ISC. The parallel resistor value is called Norton's equivalent resistance, whose value is equal to Thevenin's equivalent resistance. Both are same. Norton's equivalent resistance and Thevenin's equivalent resistance, both are same, Nana. You understand, all of you? Okay. Well, how do you find I Norton's or ISC? Replace the load by the short circuit and determine the current flowing through the short circuit. That is known as Norton's equivalent current or short circuit current. How do you find R Norton's? Same procedure of RTH, because both the values are same. Yes or no? Okay, both the values are same. Now, DC theorems. In this, where we are in DC theorems, don't forget that, because already superposition we discussed and Thevenin's we discussed. Now we are into what? Norton's theorem, right? Now look at this. Some relations in the Thevenin's and Norton's we can find. R Norton's is same as RTH. VTH is nothing but what? How do you find VTH? How do you find VTH? You are removing the load. That means the load current will become 0. So the voltage across the terminals where the load is removed, that means where the load current becomes 0, that is nothing but VTH. That's why VTH is nothing but VL where IL is 0. VL where IL is 0. I Norton's is IL where VL is 0, because you are shorting the load terminals, removing the load and replacing the short circuit. Nothing but what? Voltage across short circuit is 0. Voltage across the short circuit is 0. This voltage becomes what? None of VL is equal to 0. The current, load current where VL is 0 is nothing but Norton's current. Okay. The voltage across the load where the load is removed, that is load current is 0, that is called VTH. Is it clear, all of you? Okay. It's very clear. And the ratio of VTH to I Norton's is known as the RTH. The ratio of VTH to I Norton's, because you know Thevenin's equivalent circuit, plus minus. Yes or no? And you also know the Norton's equivalent circuit. According to source transformation, when Rn is equal to RTH, then I Norton's will be easy to express. I Norton's is equal to VTH by RTH. And from this you can get what is RTH? Nothing but what? VTH by I Norton's. VOC by ISC. Okay. So according to these two relations, where VL is nothing but, VTH is nothing but VL when IL is 0, and IN is nothing but IL where VL is 0. Look at this now. When I draw a curve between IL and VL, okay, this point is the point where the line is intersecting the VL axis, where IL is 0. Now, whatever the voltage that appears across the terminals where IL is 0 is nothing but what? VTH. Similarly, this is the point where, you know, the line is intersecting IL axis. That is a point where VL is 0. But the current where IL is 0 is called I Norton's. From this, you can find easily what is RTH. Nothing but the ratio of Thevenin's equivalent voltage to Norton's equivalent current, or VOC by ISC. Very, very important, Nana. Okay, directly or indirectly, a lot of questions will come on this particular relation, VOC by ISC. Got it, okay? Now, there are many cases in the exam. RTH is required to determine in the case of dependent source problems. In the case of dependent source problems, if you want to find a Thevenin's equivalent resistance, the same procedure is applicable in the case of transient analysis also. There, if you want to find the time constant, L equivalent by RTH, or tau is equal to C equivalent into RTH. Thevenin's equivalent resistance is to be determined. When you have a dependent source network, okay, you can find using two methods. Method 1, simply use the formula VOC by ISC. You understand, okay? Simply use the formula VOC by ISC. Find VOC first, then you find ISC, then find the ratio, you will get RTH, simple. But there are certain places, there are certain situations where you cannot determine VOC and ISC, Nana. Okay? You cannot determine, undetermined sometimes. You cannot determine that. You have no chance to find VOC and ISC. In such cases, this formula does not work. You have to go for method 2. That is called volt-amp method. According to volt-amp method, the first step what you have to do is you suppress all independent sources, deactivated. What do you mean by that? Your suppressing means you are replacing all independent energy sources by their internal resistances. Following all of you? Okay. Well, now here you connect one voltage source or current source, whichever you like. I'm connecting current source with the value of I. I'm assuming that the voltage across the current source will be V. Now using any technique, either mesh analysis or node analysis, mostly we go for the node analysis and find some relation between V and I. V is equal to something into I. This something is nothing but Thevenin's equivalent resistance, because you have deactivated all independent energy sources. You can't deactivate the dependent source, Nana. Yes or no? Okay, you can deactivate only independent sources. When you deactivate all independent sources and find the resistance across the terminals where the load is removed by connecting one source, okay, and finding the relation between the voltage and current, that resistance is nothing but what? Thevenin's equivalent resistance. When you deactivate all independent energy sources, Nana, the resulting network is assumed to be passive. The resulting network is assumed to be passive. Sir, what is the guarantee that the resultant network is passive because there is a dependent source? I am saying that you assume that it is a passive. You understand, all of you? Okay. Now, after assuming that the resulting network is passive, put your efforts by connecting the voltage source or current source, by connecting voltage source, current source, find the relation between these two and find that V to I ratio nothing but RTH. Now, if that RTH is a positive value, then the assumption is correct, that is a network given is a passive network. If RTH is a negative value, please understand clearly, nowhere it is written in the book, I am telling you. These kind of concepts are not written in the book, I am telling you. I just repeat once again. You are suppressing all independent sources and the given network is assumed to be passive. Okay? What is the guarantee that is a passive network? Passive means what? It absorbs the power. Active means it will supply the power. Yes or no? Now find RTH. If RTH is positive, if RTH is positive, then the given network is passive network. If RTH is negative, then the given network is what? Active network. It will supply the power. Passive network absorbs the power. Active network supplies the power. That's why I have written here. In case of dependent source network, sometimes the RTH may be negative. Negative resistance indicates the given network or circuit supplies the power. Okay? Instead of absorbing the power. That means what is the active network? If it is a positive resistance, then it is called what, Nana? Passive network. Negative resistance is an active network, you can call it. Is it clear, all of you? Please respond in the comment box, all of you. I think you are active, right? Hope you are following this. Please respond quickly. This concept, did you find anywhere? Have you heard about the RTH positive negative values and the interpretation of negative and positive values of RTH? Have you heard anything about it? All of you, please let me know. Yeah. Now, Karan Shah, Hindi, no please, I'm sorry. Yeah, Ravi Shankar, Bhaskar Lakshmi. Bhaskar Lakshmi understood. Ravi Shankar, I would like to repeat. No. See, you are actually trying to say that you are dealing with what? Dependent source networks. A network which consists of a dependent source. How do you find RTH? Method 1 is what? This formula. But sometimes this formula fails because sometimes you cannot find VTH and ISC, I Nortons. That is why I told you to follow old-time method. But in the old-time method, Ravi Shankar, are you following? But in the old-time method, yes, Hema, very good. So, Ravi Shankar, but in the network, you are suppressing all independent sources. You have to suppress. If you want to apply old-time method, you have to suppress independent sources. When you suppress all independent sources means what, Nana? Replacing all independent sources by their internal resistances. When you replace all independent sources by their internal resistances, the resulting network is assumed to be passive. No guarantee that is going to be passive, but it is assumed to be passive. Okay, now you connect one voltage source or current source, whichever you like, and find the relation between this V and I. Okay, then the ratio of V to I is nothing but RTH. Now, you assumed it is a passive network, right? There is no guarantee it is a passive network, but you can conclude after finding RTH value. If RTH is a positive value, then the given network, whatever you assume it to be passive, right? It remains passive only. If that RTH is negative, sometimes you find negative resistance also in the case of dependent source problems. Only in the case of dependent source problems, you will find negative resistance. Sometimes, not all time, depending upon the circuit, depending upon the polarities of the dependent source connections, you may get negative resistance. If it is negative resistance, then the given resulting network after suppressing all independent sources may be active network. Now it is clear, Ravi Shankar? Okay? Well. So what does that negative resistance indicate? Is it the active network means what is supplying the power instead of absorbing the power? Well. No, don't remember like that. Positive supply? No. Don't remember like that. I'll tell you how it is. Look at this. Ravi Shankar, for you. You started with an assumption that let me give you clearly. You started with an assumption that this is a passive network. And to find the resistance, you connected one voltage source or current source, whatever you can call it. Clear? This is V, this is I. Okay, I'm taking voltage source for easy understanding purpose. This is a passive network. Assumption Anna. No guarantee. Well, this is passive because it is taking the current, right? The polarities are plus minus. The current is entering into positive. Therefore, it is a passive network. I'm assuming it is absorbing the power. Whereas the source is supplying the power. Is it clear? First, you tell me, Ravi Shankar. Very good. Look at this. But the value which you got here is, let us say, okay, minus 7.5 ohm, let us say. Minus 7.5 ohm. Now, this minus 7.5 ohm, look at this. Can I write something like this? V by I is equal to minus 7.5. Can be written as V by minus I is equal to 7.5. Is it okay now for you? This is now 7.5 I'm writing. But now I'm writing what? No, this is V, but this is minus I. Is it clear, Ravi Shankar? Is it clear? Well, very good. Look at this. Now, minus I upward direction is nothing but what, Nana? I in downward direction. Is it clear? Please respond quickly. Is it okay now? Look at this, what is happening? The source is absorbing the power. When source is absorbing, the network is supplying. Okay? The network is supplying. Clear, all of you? I started with an assumption that it's a passive network because it was absorbing the power. The source was supplying the power. The network was absorbing the power. But because of the negative resistance, at the end I realized that the source is not supplying. The source is actually taking the power. The network is supplying the power. That is why I call it as now active network, not a passive network. Okay? Well, so RTH positive, it means it is a passive network. RTH negative, it means the given network is active network. Clear, all of you? Okay? Yeah, when current flows from positive means it supplies. Yes, exactly, Nana. Hema, that is true. Current actually initially it is leaving from positive, therefore it is the source is supplying, but the network is absorbing. Yes or no? But the end, what is happening? The current is entering into positive, okay? And whereas as far as network is concerned, the current is leaving from positive, but as far as source is concerned, the current is entering into positive. Therefore, the source is absorbing, network is supplying. Very good, Ravi Shankar, you got it clear. Okay, very good, very good. Hema, is it clear, Nana? Very good. Shall we now start with the maximum power transfer theorem? Very interesting one. Very interesting one. Okay, maximum power transfer theorem. Maximum power transfer theorem generally you apply to the circuits which consists of, okay, a load, a variable load. A load must be variable, otherwise maximum power transfer theorem is not applicable. Clear? Okay, well, the load must be variable. So any linear bilet network can be replaced by a single equivalent practical voltage source according to Thevenin's theorem. And from this, you can derive an expression for RL for which it receives the maximum power, condition for maximum power. The first point in the maximum power transfer theorem to be remembered is that the load must be variable, otherwise the maximum power transfer theorem is not applicable. You want to supply maximum power to the load by varying the load. I repeat once again, you want to supply maximum power to the load by varying the load, then only it is a maximum power transfer theorem. Otherwise, it is not a maximum power transfer theorem. Okay, well. Let us take different cases. The load might be a resistive load, load might be a current source, load might be a voltage source, load might be any circuit also, combination of some different elements. Load might be some circuit also, some network also might be a load. Okay, one network, okay, is acting like a load to another network. This is a load. This is a source. Source consists of so many elements, load consists of so many elements. It might be. I am taking different cases. First I take a resistive element, then I'll take current source, then I take voltage source, and just see the formulas here. RL is equal to RTH is the condition for maximum power transfer in case of resistive load, and the amount of maximum power that can be transferred to the load will be VTH square by 4 times RTH. Okay, and the efficiency in this case for maximum power condition, efficiency under maximum power condition will be half, nothing but 50%. The 50% efficiency. Clear? Well, case 2, load is a current source now. Load must absorb the power, receive the power. That's why I've intentionally taken the current source in the downward direction, because the current is entering into positive terminal. Don't say it is leaving from positive terminal, it is entering into positive terminal. Okay? Well. Now, what is the condition for maximum power transfer in this case when you are trying to supply maximum power to the load, that is current source, by varying the current source value? I am trying to vary the current source value here. IL is equal to 0 ampere, 1 ampere, 2 ampere, 2.5 ampere, 10 ampere, 11 ampere. Like that I am just proceeding. At one particular value of current, it receives the maximum power. That is called condition for maximum power. The formula is like this. There is a derivation for it. Okay, I'm not going to explain the derivation. If you have any doubt, I'll send you the derivation. I told you already that. You please interact with me here. This is my Telegram group. Okay, please interact with me in the Telegram channel. Okay, you can join and you can have a chat. IL is equal to VTH by 2 times RTH, nothing but condition for maximum power transfer. And this is what the maximum power that can be transferred to the load under this particular condition. Load is a current source in this context. It is very important, Nana. There are a couple of times the questions have been asked on the load current source. Some people remember only when the load is resistive element. But when there is a current source, you have to remember the formula also. Or you can derive it easily. Okay? Well, now the load is voltage source. The load is now voltage source. Tell me here, when the voltage source is taken, look at this. I have taken directly, the polarity is intentionally like this because the current should enter into the voltage source, positive terminal, so that it will absorb the power. Load must always absorb the power. Here the load is voltage source. Load must absorb the power. Yes or no? The condition for maximum power transfer here is VL is equal to VTH by 2, half of Thevenin's equivalent voltage is the condition for maximum power. Maximum power transferred to the load when VL is variable, it is VTH square by 4 times RTH. One important observation is that this formula does not change. Look at this. This formula does not change. But these conditions are changing. RL is equal to RTH, IL is equal to VTH by 2 times RTH, VL is equal to VTH by 2. These formulas are changing. Clear? Maximum power transfer theorem is very, very important, both in DC circuits as well as AC circuits. Okay? So this is all about DC circuits. Now quickly we move on to the AC circuits. Okay? AC quantity you know how to define, right? It is a quantity whose both magnitude and polarity change with respect to time. Both, polarity as well as magnitude. You take sinusoidal, the magnitude is changing and polarity is also changing because it is positive terminal. This is a positive polarity, it is a negative polarity. Okay, direction or polarity is changing. Whereas DC, this is a DC or AC? Tell me all of you. DC or AC? Is it DC or AC? Tell me. The magnitude is changing, but the polarity is not changing, right? This is positive, this is also positive. Yes or no, all of you? Okay. So this is a DC. Of course, it is not pure DC, but DC. Okay. Any quantity whose both magnitude as well as polarity change with respect to time, then that is called AC quantity. Any quantity whose polarity does not change with respect to time, magnitude may or may not change, doesn't matter. That is called DC quantity. I think all of you clear with this particular definitions, right? Okay. How do you find the average value for periodic waveforms? The same waveform quantity is changing at regular intervals. We can call it what? Periodic waveforms. For periodic waveforms, you need to find average value, RMS value, form factor, peak factor, important formulas. Okay, average value is nothing but 1 by T, integral 0 to T, V of T dt. Okay. And integration 0 to T, V of T is always expressed as what, Nana? Area under the curve. You can easily solve the average value. You can easily find the average value for triangular shape, okay, rectangular shape, or trapezoidal shape. Yes or no, all of you? You can easily find simply by finding the areas. Don't unnecessarily go for the integration of the functions or the expressions. Okay? Well. But you know that average value is defined based upon what? The average value is defined based on the amount of charge transferred to the load from the source. This is very, very important. On what basis you are defining the average value? You are defining the average value based on the amount of charge that is transferred to the load from the source. It's a very, very important point. Okay? One mark questions, GATE or ESE or any government job exam you come across, this point is very, very important. Following, okay? Well, RMS value, root 1 by T, integration 0 to T, V of T whole square dt. Note, RMS value is the measure of heating effect. This is actually how much amount of charge is transferred from load to source to load. Based on that, average value is defined. But based on the heating effect, the RMS value is defined. Okay, this is also very, very important point. Now, what is the form factor? Nothing but ratio of RMS to average value. Ratio of RMS to average value. Generally, for symmetric waveforms, the average value will become what? On a 0. But when average value is 0, the form factor RMS by 0, it becomes infinity. But this is not a practical value. Okay, average value will be 0, but form factor is not infinity. That's not a practical value. Form factor never becomes infinity. That is why, in order to determine the form factor for all symmetric waveforms, we determine only for a half cycle. The average value is determined only for a half cycle instead of full cycle. This is very, very, very important point, Nana. You understand, all of you? the form factor when you find for any symmetric waveform, the average value must be calculated only for a half cycle. Because for full cycle, average value becomes 0, form factor becomes infinity, but form factor infinity is not a practical value. You understood, all of you? So important conclusion is that for all symmetric waveforms, average value is 0, but symmetric average value is 0, but form factor is not infinity. It's a finite value. For that, you need to find only for a half cycle, not for a full cycle. Is it clear, all of you? Well, coming to now, when you take the resistive element, you know that, okay, you know that voltage across the resistor and current through the resistor both are in phase. The phase angle difference between the voltage across the resistor and current through the resistor is 0. But current through the inductor always lags behind the voltage across the inductor by 90 degrees. Current lags the voltage by 90, or voltage leads current by 90, or current leads voltage by 270. Yes or no, all of you? Or voltage lags current by 270. Anything is okay. Once you got one statement, then you can get the other 3 statements easily. The first most important statement to be remembered is what? Current through the inductor lags behind voltage across the inductor by 90 degrees. Is it clear? Okay? Well, in case of capacitor, current through the capacitor leads voltage across the capacitor by 90 degrees. Clear, all of you? Okay? Current through capacitor leads voltage across the capacitor by 90 degrees. Is it clear, all of you? Good. Now, average power absorbed by any pure inductor or pure capacitor is 0. Okay? A pure inductor, in the first half cycle, it takes the power. Second half cycle, it discharges the power. So, what is the total average power? Average power generally you calculate over one complete cycle. First half cycle, it takes the power. Second half cycle, it gives back to the source. Okay. Similarly, inductor also, capacitor also. Inductor as well as capacitor, both. Suppose if inductor takes the power in the first half cycle, then the capacitor gives back to the source. The second half cycle, if the inductor is giving back to the source, the capacitor takes the power. Both are opposite directions actually. You understand all? Both are opposite directions. But over one complete cycle, in the first half cycle, if it takes the power, the second half cycle, it will give back to the source, both inductor as well as the capacitor. But only thing is what? When inductor takes, capacitor, gives. When inductor gives, the capacitor takes. The direction is different. But first half cycle, if one takes the power, the second half cycle, it gives back to the source. So the average power absorbed by the pure inductor and pure capacitor is always 0. And one more important point is that the frequency of the power is double that of either current or voltage. If voltage frequency is 50 Hz, the power frequency is 100 Hz. If current frequency is 50 Hz, the power frequency is 100 Hz. But voltage frequency, current frequency, both will be same across the system or across the total system. There is no difference at all. But the power frequency always is double that of what? The current and voltage. It's very, very important. Here the printing mistake, Nana, please don't mind. Okay, the typographical mistake. The power frequency is always twice the frequency of voltage or current. But voltage frequency, current frequency, the entire power system, it is same, Nana. Okay. Now, V of t is equal to V max sine omega t plus or minus alpha is a general sinusoidal expression. If it is plus alpha, okay, and minus alpha, if you see, minus means it is lagging angle, plus means it is a leading angle, okay, and it can be expressed in the complex numbers as what? V max by root 2 plus or minus alpha, RMS value. This is an instantaneous form or sinusoidal form. This is the RMS form or a complex form. Okay, any sinusoidal form can be expressed as a complex form. Okay, RMS form. S is equal to V into I. Apparent power is nothing but sum of complex addition of active and reactive powers, or else you can say apparent power is nothing but the product of RMS voltage and complex conjugate of RMS current. Complex conjugate of RMS current. Here P plus or minus JQ, the positive indicates for inductive load, the negative indicates for capacitive load. Positive is for inductive load, negative for capacitive load. Is it clear all of you? Complex power, Nana. I hope you remember this. Okay. Coming to now RL series circuit. R, JXL, VR and VL. The formulas for impedance is nothing but Z is equal to R plus JXL, but Z square will be what? R square plus XL square. V is equal to VR plus JVL, with an assumption that the current is taken as reference. Okay. Then V square will become VR square plus VL square. S is nothing but P plus JQ. Then S square is nothing but P square plus Q square. Is it clear all of you? Very simple formulas, Nana. The phasor diagram you can take here. First you draw the current. Then VR is equal to I into R. Okay. VR is in phase with current. And VL leads the current by 90 degrees. Okay. Then the voltage, the resulting voltage can be taken as V, is nothing but what? VR square plus VL square square root. Okay. Similarly, the impedance can also be expressed here. This is what the power factor angle. Angle difference between the voltage and current is always what? Power factor angle. Cosine of that angle is nothing but what? Power factor. Okay. Cosine of that angle is nothing but what? Power factor. Impedance angle, theta, R and XL. Okay, and this is Z. This theta is nothing but what? Impedance angle. Impedance angle and power factor angle both are same. Theta is equal to phi. Power also, active power, reactive power, of course always maintains 90 degrees here. This is what? Apparent power. This is what? Power angle. Power factor angle, impedance angle, power angle, all are same. Got it? Okay. Okay, power factor angle, impedance angle, all are same, Nana. Clear all of you? Okay. Hope all of you following. Very simple. These are all RL series, RC series and RLC series. Then RL parallel, RC parallel, RLC parallel. Similarly, Z is equal to R minus JXC, V is equal to VR minus JVC, S is equal to P minus JQ. And always remember V square is equal to VR square plus VC square. Okay. If VR is equal to 4 volts, or 3 volts, and VC is equal to 4 volts, what is the value of V? What is the value of V? You can't say 3 plus 4, Nana. This is wrong, right? What is V now? Root 3 square plus 4 square, nothing but 5 volt. Because you are dealing with RMS values. The meter which you connect, the MI type meter, generally you connect MI type meter, the V1, okay, and here it is a V2, okay. This V1 and V2 reads always RMS magnitudes. When you know the magnitudes, generally the actual expression is something like this. Magnitude V square, magnitude VR square, plus magnitude VC square, Nana. This is what the expression actually you are supposed to maintain. Okay, I'm not always maintaining that, magnitude symbol, but it is by default there, okay. Similarly, the phasor diagram, current is taken reference, voltage, VR, and then VC. Okay, this is VC, and this is what the total V. Okay, you will be getting VR square plus VC square. Similarly, Z also. Similarly, the power also. So, power angle, impedance angle, power factor angle between voltage and current. The phase difference between voltage and current always is said to be power factor. Cosine of angle, that angle is nothing but power factor. The cosine of that angle is nothing but the power factor, and the angle difference is nothing but what? Power factor angle you can call it. Is it clear, Nana, all of you? Okay. Now, very simple, okay. Now, RLC series circuit. Z is equal to R plus J XL minus XC. VR is equal to VR plus J VL minus VC. S is equal to P plus J QL minus QC. V square is equal to VR square plus VL minus VC whole square. Are you able to recollect all these formulas? Clearly, all of you? Are you able to recollect all these formulas from DC and AC circuits I am discussing now? Well, please respond all of you in the comment box. Well, now, if XL is greater than XC, then the circuit is said to be inductive circuit or lagging power factor circuit, Nana. Lagging power factor circuit. If XC is greater than XL, it is called capacitor circuit or leading power factor circuit. If XL is equal to XC, then you can call it resistive circuit or unity power factor circuit. Is it clear, all of you? Very good, Bhaskar Lakshmi, okay? Well, now coming to the parallel circuit, I'm directly writing now, I think you are able to follow. This is G, this is minus JBL. This is the current source, Nana, okay? Current source I and the voltage across the current source is capital V. Current divides now IR and IL, okay? Y is equal to G minus JBL. Y square is equal to what? G square plus BL square. I is equal to IR minus JIL with an assumption that this voltage is taken as a reference phasor. Always remember, in the AC circuits, one particular phasor must be taken as a reference phasor. In series circuits, we have a common practice, current is taken as a reference phasor. In parallel circuit, it is a common practice that voltage is taken as a reference phasor. Got the point? Okay. So I square is equal to IR square plus IL square. S is equal to P plus JQL. S is equal to P plus JQL. Now when you construct the phasor diagram, the voltage is taken as a reference. This is IR. This is IL, which lags behind the voltage. But the total current is what, Nana? Here total current is I is equal to IR square plus IL square. This is what the power factor angle. Similarly, you can go for what? Okay, the admittance angle. Okay, admittance. How the admittance will be, Nana? Because Y is equal to G minus JBL. G minus JBL means nothing but A minus JB form. A minus JB means this is a real part, this is an imaginary part. Okay, this is a minus, negative, right? The value will be in the fourth quadrant. Okay, this is G, this is minus JBL, this is nothing but Y. This is G, this is BL, this is Y. This is what theta. So triangle is downward. For inductive circuit, impedance triangle is upward, admittance triangle is downward. Whether it's series, parallel, doesn't matter. Capacitive circuit, impedance triangle is downward, admittance triangle is upward. You understand? Okay. Power triangle, for inductive circuit, it is upward. For capacitive circuit, it is downward. Is it clear, all of you? Very clear, all of you. If you have any doubt, I'll explain again. Ravi Shankar, very good. Okay. But if you please respond quickly if you have any doubt on what I've explained. Okay. For inductive circuit, impedance triangle upward, admittance triangle downward, power triangle upward. This is for inductive. For capacitive circuit, this is Z, this is Y, this is P. Okay. For capacitive circuit, impedance triangle is downward, admittance triangle is upward, power triangle is downward. You have to remember all these things. This is Z, this is Y, this is P. But this is for capacitive. Clear? This is for capacitive. If you have any doubt, I'll clarify again. Please let me know. Well, so this is what actually you are going to get. Y is equal to G minus JBC, whereas here G minus JBL. Okay, I is equal to IR minus JIC. S is equal to P minus. This is P minus JQ. See, no? This is P plus. This is P minus. Okay, same phasor diagram. Clear? Very good. Very good. Very good. Very good. Voltage is taken as reference again here. IR, IC, and I. I is equal to IR square plus IC square square root. This is what power factor angle. Okay. perfect triangle. I told you already that the admittance triangle will be upward because y plus jbc. This is y plus nana. A mistake, please rectify it. G plus jbc. Y is equal to g plus jbc. Whereas here g minus jbl. This is g plus jbc. So triangle is upward. Power triangle is downward. This is P, Q, C and S. This is G, B, C and this is Y, theta. That's it. Clear? Okay. Well, one important observation in RLC parallel. This is RLC parallel. Okay. Y is equal to G plus J, BC minus BL. I is equal to IR plus J, IC minus IL. This is what the formula. This is square, Nana. Okay. IC minus IL square. Some typographical mistakes are there. Be careful. Okay. S is equal to P plus J, QC minus QL. Okay. Now, in the case of series circuit, you observe that XL greater than XC, then it is called inductive. Okay. XC greater than XL, it is capacitor. You understand? This is for RLC series circuit. But when it comes to the parallel circuit, all of you please respond. All of you please respond. In the case of RLC parallel circuit, okay, if BL is greater than BC, is it inductive or capacitive? Yes. Is it inductive or capacitive? If BL is greater than BC, is it inductive or capacitive? All of you should respond quickly. All of you should respond quickly. Capacitive. Bhaskar Lakshmi is saying capacitive. BL greater than BC is capacitive or inductive? Capacitive, Ravi Shankar. Ravi Shankar is saying capacitive. Hema is saying inductive. Bhaskar Lakshmi is saying capacitive. Someone else, I don't read his name. Some name is Jitendra or something. Okay? Jitendra Nath, I think. Yeah. It is completely, the text is completely reversed. No problem. But I think Jitendra, right? Hope your name is Jitendra Nath, right? Okay, you are saying capacitive. Reshma saying inductive. So those who said capacitive, I know that they are trying to apply reciprocal to it because BL greater than BC means XL less than XC. When XC is greater than XL, it is capacitive. Like this they are thinking. Ravi Shankar, okay, you corrected. It is inductive, okay? Okay, fine. So XL is less than XC means it is capacitive usually. But generally you should not apply the reciprocal concept here. You should not apply the reciprocal concept here. What you have to do is, you just think here Y is equal to G plus J BC minus BL. Generally, Z is equal to R plus R minus JX. In this, plus is for inductive, minus is for capacitive. Y is equal to G minus R plus JB. Here, negative is for inductive, positive is for capacitive. You agree? You agree with this, all of you? You agree with this one and this one? In inductive, plus is for, in impedance formula, plus is for inductive, negative is for capacitive. In admittance formula, negative is for inductive, positive is for capacitive. You agree? You agree, all of you? Please respond quickly. Then only I can proceed further. Then only I can proceed further. Please respond quickly. In impedance formula, positive is for inductive, negative is for capacitive. In admittance formula, negative is for inductive, positive is for capacitive. Yes. Hema, Bhaskar Lakshmi, all of you. Okay, good. Following. Now, in this case, if I take BL greater than BC, okay, BL greater than BC. Now, when BL greater than BC, when I take, BC minus BL will be negative or positive? Definitely negative. JB. This result is what? You are going to get what, Nana? Negative. Okay, that means BL minus BC you are getting. Because BL is greater than BC. Okay, I take the negative common. That is why this is now inductive. So don't apply that reciprocal concept. For series circuit, you must compare always reactances. For parallel circuits, you must compare always the susceptances. Because B is nothing but the susceptance. Okay? B is nothing but what? Susceptance. So is it very clear, all of you? Very good, very good, very good. Bindu Taringini, very good. Ravi Shankar, you got it. Bhaskar Lakshmi got it. Hema got it. Okay. Jitendra, Nath, you got it or not? Tell me. You said capacitive. Still you are in capacitive or inductive? Please tell me. Very good, very good. Is it clear? Well, so for a series circuit, you must always compare what? XL greater than XC, XC greater than XL, like that. I can write something like this to remember easily. Conclusion I would like to write. XL greater than XC, nothing but BL less than BC is inductive. XL less than XC, nothing but BL greater than BC is capacitive. All of you please note down this, very, very important. For parallel circuit, BL greater than BC, nothing but what? XL less than XC is inductive. Because we don't know in the exam whether he will provide you the inductance values or susceptance values, we do not know. But one thing is clear in our mind that if it is a series circuit, we have to proceed with the reactances. If it is a parallel circuit, we should proceed with what? Susceptances. So look at this, I started with the reactances for series circuit, and for parallel circuit, I am proceeding with what? Susceptances. Look at this, there are susceptances. Okay, BL less than BC, which is nothing but XL greater than XC. Okay, this is nothing but what? Capacity. So always we have a habit of remembering, always we have a second order equation of RLC in series circuit. Second order, RLC is nothing but second order, no Ravi Shankar? Second order only. RLC is nothing but second order. RL is a first order, RC is the first order, RLC is always second order. Whether it's a series parallel doesn't matter. Okay? Well. Okay? So XL greater than XC is inductive, people remember, but that is only for series circuit. Now here XL greater than XC for a parallel circuit is becoming capacitive because BL less than BC or BC greater than BL is a capacitive here. Clear? Okay? Very clear, right? Very good. So that's why I have highlighted here. Now one more important formula, there is a load, inductive load. Okay, a practical inductor. Okay, this theta is nothing but what? The angle of this impedance, Z is equal to Z at an angle of theta, Nana. Okay, impedance angle, load angle. Load angle is nothing but what? The phase difference between the load current and the load voltage. Okay, the angle difference between V3 comma IL is nothing but theta. That is nothing but what? Load angle, impedance angle, okay, power factor angle, all are same. In such case, if a resistive element is connected in series with this practical inductor and you are connecting some voltmeters V1, V2 and V3, and now V1, V2, V3, now you have a relation. If you know the angle of this particular load, then you can express V1 square is equal to V2 square plus V3 square plus 2V2 V3 into cos theta. This cos theta can be determined now V1 square minus V2 square minus V3 square by, okay, by 2 times V2 V3. 2 times V2 V3. Is it clear, all of you? Okay, in the exam, literally, in one of the previous years, if you go through the papers in the GATE examination, he asked this angle. What is the power factor of the load? He asked. Power factor of the load is nothing but cos theta. He gave the voltmeter readings V1, V2, V3. Simply substitute here and get the value of this particular value, Nana. This is nothing but power factor of the load. Clear? This is a very, very important formula. So this formula 1 series is very helpful, I'm telling you. Okay, I'm not doing any problems here. In next upcoming sessions, probably I can do some problems. Okay, but you please put in the comment box, okay, in the network theory, which particular chapter you are facing the problem. Okay, I can definitely discuss. Majority of the people, whichever you ask, okay, I will have a discussion in the near future. Okay, I'll talk to my team and I will try to arrange. I will ask them to arrange the lecture, whichever the topic. I already had discussed, the transient analysis in detail. In detail, I discussed around 5 to 6 days I spent. Please go back to my videos. You can please access those videos. You will understand the transient analysis in a very, very, very detailed manner. Okay? Well. Clear? Well. Now, AC theorems, maximum power transfer theorem we will discuss, because Thevenin's theorem, Norton's theorem, superposition theorem, all theorems are same for DC as well as AC. But what is different? What is different for AC circuits here is maximum power transfer theorem is different for AC and DC circuits. The maximum power transfer conditions for AC circuits is different from the DC circuits. Okay? Where Nana? Current. Which current? Okay, here if you want to find the current, Bindu Tarangini, if suppose current is asked here, certainly these values must be known, Nana. Generally, if voltage value and this impedance value, if you know, then only it is possible to find the current. Otherwise, it is not possible to find the current. So such kind of complications won't be created. If he is asking current, means he will have a clarity. What is the data to be provided to you, right? What is the data that should be provided to you? He has a clarity on that. Don't worry about that. You can find that once you have voltage, this impedance, then you can find the current. I is nothing but V by Z, Ohm's law. Well, maximum power transfer theorem, I am taking different cases. This is what the circuit you have, because any linear bilet network can be replaced by an equivalent Thevenin's equivalent circuit. Yes or no? This is a Thevenin's equivalent circuit. This is a Thevenin's equivalent circuit. This is a Thevenin's equivalent circuit. Okay? Very good. So here, Thevenin's equivalent circuit is mandatory. When you are applying for maximum power transfer theorem, Thevenin's equivalent circuit is mandatory. Okay? Well, now, let me take this load. There are different loads. Suppose if I take load is of resistive load, pure resistive load I have, then this is nothing but RL is equal to magnitude of Z Thevenin's. For example, Z Thevenin is equal to 3 plus J4, then RL value is magnitude of 3 plus J4, nothing but what? Root 3 square plus 4 square, nothing but 5 ohm, is the condition for maximum power transfer. That means if you are fixing this RL value at magnitude of Z Thevenin, then that load will receive the maximum power. That maximum power value that is received by the load will be, this is what the formula, VTH square into RL by RTH plus RL square plus XTH plus XL square. Okay. Similarly, the second case is ZL is equal to RL plus JXL. I am varying both resistive element as well as the reactance element. Both resistance and reactance both are variable. Okay. Then ZL is equal to what? Complex conjugate of Thevenin's equivalent impedance is nothing but condition for maximum power transfer. For example, you have ZTH is equal to 3 plus J4. Then when you fix the value of the load to be ZTH conjugate, conjugate is nothing but what? 3 minus J4. Then the load will receive the maximum power. In such cases, the maximum power value PL max will be VTH square by 4 times RTH. This is also very, very important formula. Okay? So in AC circuits, you must immediately check whether the load consists of a pure resistive element, then use this formula. If the load is consisting of both variable resistance and variable reactance, then use this formula. Clear all of you? Okay? Very good. Now, coming to the resonance, most important topic, high weightage topic, most important topic, high weightage topic, that is RLC series resonance. Okay? So, and of course, parallel resonance. Resonance topic we are going to discuss here. Series resonance as well as a parallel resonance. The condition for resonance is nothing but what? The imaginary part of the total input impedance is what? 0. Or total admittance is what? 0. Okay, the phase angle difference between the voltage and current is what? 0. Yes or no, all of you? The phase angle difference between voltage and current phasors is 0. The power factor must be unity. Unity power factor, phase angle difference between voltage and current is 0. The imaginary part of input impedance is 0. The imaginary part of input admittance is 0. All are nothing but condition for resonance. Yes or no, all of you? Condition for resonance. The resonant frequency formula for RLC series resonance is that 1 by root LC. And these are the important formulas. Okay, these are the important formulas for half power frequencies. Half power frequencies. When you find the current, and this is what the frequency, when you draw a 3 dB line, these two are called what? Half power frequency, half power, half power points, P1 and P2, and these are all the frequencies, half power frequencies. The difference between these two is called bandwidth. The bandwidth is nothing but omega 2 minus omega 1, okay, nothing but R by L. The formula is what? R by L. Omega R, omega 1, omega 2 relationship. It is the omega R is geometric mean of omega 1 and omega 2. Geometric mean. Geometric mean. Okay. Selectivity is inversely proportional to bandwidth. Quality factor is inversely proportional to bandwidth. Therefore, quality factor is directly proportional to selectivity. Higher the selectivity, higher the quality factor. Or higher the quality factor, higher the selectivity. Lower the bandwidth, higher the selectivity. Got the point, all of you? The bandwidth must be as smaller as possible. The difference between the electric circuits, communication systems, the difference between the communication systems and the control systems. The difference between communication systems and control systems. In communication system, the bandwidth must be as smaller as possible because selectivity is inversely proportional to bandwidth. In control systems, when you design a system, control system, the bandwidth must be as larger as possible because the rise time is inversely proportional to the bandwidth. For any control system, a good control system, the rise time must be smaller. For rise time to be smaller, the bandwidth must be higher. For any communication system, the selectivity, must be, selectivity must be higher or larger. For that, the bandwidth must be smaller. This is for control systems. This is for communication systems. You understand, all of you? The difference between the control systems and communication systems, you understand, all of you? Bandwidth point of view I'm talking about now. Okay, well. So quality factor formula, very clear. XL by R or omega R L by R or 1 by omega R CR, or quality factor can also be expressed using this formula. This is very popular formula, 1 by R root L by C. Now, in the series circuit, VL and VC are the voltage across inductor and capacitor, okay, the quality factor must be very much higher, okay, than 10. Okay, high quality factor you must maintain. It is minimum 10 nana. Okay, maximum anything it might be, like as higher as possible. The quality factor must be as higher as possible. Okay, then what happens here? VL and VC is equal to Q into V. Because the quality factor is very much greater than 10, therefore always remember at resonance condition VL is equal to VC, which is very much higher than, which is very much higher than what? V. You understand, all of you? Okay, very good. VL is equal to VC, which is very much higher than V, nana. For high quality factor, when you take for high quality factor, omega 1 will be expressed as omega R minus bandwidth by 2. Omega 2 is nothing but omega R plus bandwidth by 2. And finally, from these two, you can express that omega R is equal to omega 1 plus omega 2 by 2. This is nothing but arithmetic mean of omega 1 and omega 2. But this expression is valid for high quality factors only. Okay, high quality factor. Now, another important formula is that VR is equal to V and VL is equal to JQ into V and VC is equal to minus JQ into V. Therefore, because VR is equal to, this is very important, Nana. Okay, this is very, very important. VR is equal to V. Under resonance condition, the total voltage, if you see the phasor diagram, this is I and this is VR and this is VL and this is VC. Okay, under resonance condition, these two get cancelled. Finally, the total voltage will become what? VR is equal to V. Okay, VR is equal to V. Quality factor is nothing but VL by V. Nothing but VL is equal to Q into V, Nana. That is JQ into V. VC is equal to minus JQ into V. Okay, therefore, if you add VL plus VC will give you what, Nana? VL plus VC is nothing but plus JQ into V minus JQ into V will get cancelled. Finally, you will get what? 0. And VR plus VL, nothing but what? VR plus VL, nothing but VR is nothing but V plus JQ into V. Okay, so you can take V common. Yes or no? V common is nothing but 1 plus JQ. Yes or no? Okay, when you take magnitude here, magnitude of VR plus VL, then magnitude V root 1 plus JQ or 1 plus Q square. 1 plus Q square. I hope you are following this, okay? I hope you are following this. Similarly, VR plus VC also will be same. Therefore, you know that 1 plus Q square will be approximately equal to Q square. Of course, root is there, therefore it becomes what? Q only, but Q is higher. That is why VR plus VL magnitude is very much higher than V and VR plus VC is very much higher than V. Exactly on these particular formulas, couple of times the questions have been asked in the GATE examination and of course ESC examination only based on these formulas. Which of the following is true or which of the following is not true? Like that, he will give several conditions about RLC series resonance. You must be able to answer these questions. You understand, all of you? Okay? Yeah. Now, since RLC circuit is a second order circuit, for second order you have a damping ratio, yes or no, all of you? Damping factor. Eta you call it. Okay, eta is greater than 1 overdamped system, eta is equal to 1 critical damped system, eta is less than 1 but greater than 0, it is underdamped system, eta is equal to 0, zeta, or you can call it zeta otherwise, okay, zeta is equal to 0 is called undamped system, yes or no, all of you. So the zeta and quality factor relationship is also very important, 1 by 2 zeta. There was one question in the GATE earlier, it was asked on this particular formula, zeta and Q. Okay, he will give you quality factor and he will ask you to find the zeta value. Or he will give you a second order system and he will ask you the quality factor. For second order system, can't you find zeta value, Nana? Easily you can find the zeta value. S square plus 2 zeta omega n plus omega n square. From that, can't you find zeta value? You can find the zeta value. Find zeta, then find Q value. Q is nothing but 1 by 2 zeta only. That's it. Very, very simple and easy to calculate. Okay, these are all very important. Resonance is a very important topic in the AC circuits, Nana. Okay, very frequently you are getting the questions in the resonance. Now, one more important thing is that there are certain, waveforms you must remember. This is what VC, this is what VL. Voltage across the inductor and voltage across the capacitor will also vary sinusoidally, right? So this is what the frequency where the voltage across the capacitor becomes maximum. This is what the frequency where voltage across the inductor becomes maximum. Okay. This is what the frequency where VL is equal to VC, nothing but omega R. Okay. So omega C is nothing but frequency at which voltage across the capacitor becomes maximum. Omega L is nothing but frequency at which voltage across the inductor becomes maximum. For that also you have a formula. Please remember these formulas. You have no other way. You have to by heart. In the entire network theory, there are few places where you can by heart the formulas. These formulas are to be by hearted. You can't take any chance. You can't really do research in the exam, I'm telling you. You understand, all of you? Okay? You can't take any chance. Now, for series resonance, what happens here is, for frequency less than resonance frequency, when the frequency is increasing, impedance decreases, admittance increases, current increases, voltage across the resistor will also increase. Similarly, for frequency greater than resonant frequency, when the frequency is increasing, always frequency is increasing, but for a condition when frequency is greater than resonant frequency, impedance increases, admittance decreases, current decreases, voltage across the resistor decreases, okay, decreases. But in the first case, it is acting like a leading power factor circuit. In the second case, when frequency is greater than resonant frequency, okay, the circuit behaves like an inductive circuit or lagging power factor circuit. First here it is leading power factor circuit, here it is a lagging power factor circuit. When F is equal to FR, minimum impedance point, maximum admittance point it will reach, maximum current you will get, maximum voltage across the resistor you will get. It is nothing but what? Unity power factor circuit. Got it, okay? Similarly for RLC parallel resonance also, omega R formula, omega 1, half power frequencies. These two are half power frequencies. These two are half power frequencies. These two are half power frequencies. Omega 2, formula for omega 2. Bandwidth nana, 1 by RC. Okay? Omega R is again GM of omega 1, omega 2. Quality factor formula 1 by G root C by L. And IL is equal to IC is very much greater than I. Just like VL is equal to VC, which is very much greater than V in the case of series resonance circuit. Here IL is equal to IC, which is very much greater than I. Magnitude. IR is equal to I, IL is equal to minus JQC, IC is equal to plus JQ into I. Here minus JQ into I. Then when you add IL and IC, you know that it will become what? 0. Similarly, IR plus IL will become what? Root 1 plus Q square into I. Therefore, from this we understand that because quality factor is very much greater than 10, then IR plus IL magnitude is very much greater than I. Similarly, IR plus IC is nothing but root 1 plus Q square into I. Therefore, from this you can understand that IR plus IC magnitude is very much greater than I. Omega 1 is equal to omega R minus bandwidth by 2 for high quality factors. For high quality factors, omega 1 is equal to, previous slide, okay. You can see Bindu Tarangini, you can see the previous slide from your side also, okay? You can go back, right? This is what the previous slide. Any problem, Bindu Tarangini? Please let me know if you have any problem. Omega 1, omega 2, these formulas are applicable only for what? High quality factors. And this formula you got omega 1 plus omega 2 by 2. Generally omega r is root omega 1 and omega 2. GM of omega 1 and omega 2. But for high quality factors where Q is very much greater than 10, then this is becoming what? Omega 1 plus omega 2 by 2. This is an approximate formula. This is an approximate formula. I can take omega 1 plus omega 2 by 2. This is arithmetic mean of omega 1 and omega 2. Similarly, the zeta and quality factor I told you already. And similarly, in the case of parallel resonant circuit, the currents are something like this. You tell me which slide you're talking about. This one, Nana? This one you're talking about? You can also go back. I think you can scroll back, okay? You can go back to the previous, okay, discussion, and then you can put a comment. I can understand that comment easily. Just tell me where is the problem. Now this is IL, this is IC. This is the frequency where the IL becomes max. This is the frequency where IC becomes max. Omega L is the frequency where current through the inductor becomes maximum. Omega C is nothing but frequency where current through the capacitor becomes maximum. So these formulas can be used. Very, very important formulas. Here also I told you that zeta and Q values. RLC parallel omega 1, omega 2. Okay. This is what I'm discussing now. Yes. You tell me now. What is the problem? The formulas are clear, right? Minus 1 by 2 RC plus root 1 by 2 RC whole square plus 1 by LC. Omega 2 is 1 by 2 RC plus root 1 by 2 RC whole square plus 1 by LC. Any problem? Tell me. Bindu Tarangini, please tell me. Anybody has doubts, please quickly respond. If you have any doubts, I'll clarify, okay? I think we are left with only few slides. We can close down. Bhaskar Lakshmi, no doubts. Yeah. Well, here, in the case of parallel resonance, okay, F less than Fr, for all frequencies less than resonant frequency, when the frequency is increasing, admittance will be decreasing, impedance will be increasing, voltage will be increasing, current through the resistor will be increasing. Yeah, half power frequency, Nana. Half power frequency means when you take voltage versus frequency, when you draw a 3 dB line, you call it 3 dB line. There is a concept called 3 dB line. Okay. Here, generally, the voltage becomes V by root 2 Nana. Power becomes what? Voltage square by resistance, right? So when voltage becomes 1 by root 2, V by root 2, whole square by R, okay? 1 by 2 times V square by R you are getting. Okay, this is what the power P1, okay, P1. But this is nothing but what the power at resonant frequency. Half, okay, of the power at resonant frequency. So that is why it is called half power frequency, Nana. That is why it is called half power frequency. I think now you got the point. At 3 dB line, the voltage at this point will be what? V by root 2. These two are the half power frequencies, we can call them. Okay, well, I hope you understand this. Still, if you don't understand, please, again, I told you already that Professor Muneender Gate. I can still have a lot of discussion here. This is what my Telegram group channel. Okay, you can please join there. I can give you more clarity on that. Okay, for this particular condition, it is acting like what? Lagging power factor circuit. For F greater than Fr, when frequency is increasing, admittance is also increasing, impedance decreasing, voltage is decreasing, okay, and the current through the resistor is decreasing, and the circuit is behaving like what? Leading power factor circuit. For series circuit, in this case, actually leading power factor, in this case, lagging power factor, but it is reversed in the case of parallel circuit. You must be very careful, okay? Now, for F is equal to Fr, admittance minimum, maximum impedance, voltage maximum, current to resistor is maximum, and the circuit is behaving like what? Unity power factor circuit. Got it, okay? Okay. Now, most important circuits in the resonant circuits, parallel circuit, RL and L series combination, RC and C series combination, and these two are connected in parallel. For this, what is the frequency at resonance? The formulas can be expressed as 1 by root LC square root RL square minus L by C by RC square minus L by C. This is the standard formula. Okay. Generally, you get when Y is equal to 1 by RL plus J omega L plus 1 by RC minus, okay, RL plus JXL, RC minus JXC. You rationalize and separate real and imaginary, okay, then make this imaginary part 0, then you will get a frequency. That frequency is nothing but this frequency. So I don't want to explain the derivation. I promised you only the formulas here, okay. Please don't mind because it takes a lot of time, okay. So well, we need to finish now. I think there are a couple of slides we can finish, and yeah. So this formula is very important. But for this particular circuit, the most important condition is that if RL square is equal to RC square is equal to L by C, if RL square is equal to RC square is equal to L by C, then the circuit is said to be resonant at all frequencies. Generally, when you change the frequency from 0 to infinity, when you are changing at a particular frequency, the circuit becomes resonant. That frequency is called resonant frequency. Yes or no? Okay, I repeat once again. When you take a circuit, RLC circuit, and you are changing the supply frequency from one value to other value, okay, at some steps, let us say, incremental change you are making, 0 to some infinity you are moving. At one particular value of the frequency of the supply, the circuit becomes resonant. That frequency where the circuit becomes resonant is called resonant frequency. Yes or no? Okay. But in this particular circuit, if this condition is satisfied, RL square is equal to RC square is equal to L by C. If you are able to design the circuit in such a way that this condition is satisfied, then the circuit is resonant for all frequencies. Not just one frequency, but circuit is resonant for all frequencies. You understand, all of you? Okay? Well, so this is a very, very important point and valid point, I'm telling you. Now, another circuit is called tank circuit. This is a tank circuit. That is a parallel circuit, but this is a tank circuit. Tank circuit means a parallel practical inductor is parallelly connected to an ideal capacitor. This is a practical inductor. Connected parallel to what? An ideal capacitor. Okay. So now when you find similar way, the procedure which I have explained, that you find admittance 1 by R plus JXL plus 1 by minus JXC. Okay. The rationalize, separate real and imaginary, make imaginary part 0. Finally, you will be getting the frequency that is nothing but what? 1 by root LC, root 1 minus RL square C by L, nothing but omega R into root 1 minus 1 by Q square, where Q is the quality factor. For the same tank circuit, you should also remember the dynamic impedance. The impedance offered by the circuit at resonance is called dynamic impedance. Nothing but L by RL into C. For ideal tank circuit, RL becomes 0, then Z dynamic will become, okay, infinity. That means open circuit. Infinite impedance is nothing but what? Open circuit. Okay. So this is what you can understand, okay, about the DC circuits and AC circuits, the important formulas. I hope you enjoyed the session. Please respond quickly in your comment box. Okay, I'll be very happy to see your comment box. Okay, comments in the comment box. Okay, so next session tomorrow, most interesting session I'm going to discuss. Most important session tomorrow, that is transient analysis. Most of the people will be struggling in the transient analysis, right? I'm going to spend a good amount of time tomorrow, around 2-hour session in detail. Transient analysis, two-port networks, I'm going to discuss tomorrow. The remaining topics, I think I don't need to spend much time. If possible, if time permits, I'll spend. Otherwise, but these two are the important topics, especially transient analysis I'm going to discuss, okay? You'll be definitely getting maximum benefit, okay? So please communicate to your friends also, pass on the same message to your friends, let them join, let them also get benefited out of it, okay? So thank you so much for your patient listening. Please do subscribe to the channel, okay? And you'll be getting regular updates. I told you about my Telegram group, Professor Muneender GATE. Please join this. You'll be getting the regular updates. I'll be sending you the messages and you can also have a chat, okay? Thank you so much. Thank you, Jitendranath. Thank you, Bhaskar Lakshmi. Thank you, Bindu Tarangini. Yes, Narsima CH. Thank you, Hema. Wish you good luck, all of you. Okay, we'll meet tomorrow. Bye-bye.